Here's our PID controller setup. This is the board that controls the engine. On the side we have cables of the potentiometer, and we are reading through analog input what is the value of the potentiometer. It also goes to ground, and this is our little ground bus. We have external power source. All elements come to one single ground, so that the reference point for every part is the same. And then here's our USB cable.
Initial setup is complete.
But I will explain the theory behind the PID controller. It has three components: the proportional one, integral one, and derivative one, all having their respective weights Kp, Ki, and Kd. They are all summed, and these are basic PID control. The first component, which is proportional controller, is just a force that's proportional to the error. Increasing this constant Kp would increase the speed of, in our case, of the shaft of the servo, but also lead to overshoot and instability in some cases, so like constant oscillations, for instance. Then next controller is the integration controller, which sums the well, it just takes the integral of the error, which can eliminate steady state errors, which are small errors that cannot be picked up by the proportional controller. And then lastly we have the derivative controller, which is basically a damping force, meaning it's a force opposing motion, also proportional to the speed of the shaft. Now, it's just the derivative of the error. It will decrease the oscillation and overshoot, so we will get to our desired position quicker.
The Kp value is 1. I'm moving the engine, and we see that it's not reaching the target value, or sometimes almost reaching it. Now we're gonna see what happens when we increase the Kp value. We have our integral resetting every 1 second, and every 1 second we're reading the input, so every 1 second we can change the target Kp, Ki, or Kd.
So it always takes the shortest route. We have tuned the coefficients for, in our opinion, the best values, which are Kp equal 8, Ki equal 4, and Kg equal 0.1. We have done it by going one by one, starting with Kp, and now I think it's perfect.
Here is our calculation of Ziegler and Nicholas coefficients. After adjusting the threshold for speed so that our motor moves immediately, we calculated the new Ziegler and Nicholas values, and they started to work according to how expected. Here's how they work. There is still some little oscillation when the engine reaches the desired position, but it's minimal, and we have a very small error margin, so we're very satisfied. And actually, Ziegler and Nichols outperformed, after adjusting the threshold for speed. Ziegler and Nichols outperformed us and how to perform our intuitive tuning. I'm going to shortly go through the most important parts of the code that was running on our Arduino. Apart from the standard variables, we added some extra. Temporary error is an error on the previous measuring that we used to calculate the derivative. Error sum is the integral of the error, and we needed to add engine minimal speed threshold because we discovered that until the value 30 the engine did not actually move, and the variable PID is the current value of our PID equation. I'm going to skip to the loop part. So the first for loop is used so that every 50 cycles we can read input, and our cycle is 20 milliseconds, so that means that every second we read the input. We use the timer for our intervals. Every time the absolute value of the integral of the error is bigger than 255, we will reset it. We save the error from before. We calculate the new value of error. Now, in order for the engine to go the shortest way, so not to go around always clockwise, but to choose the shortest path to the target position. So here we calculate the derivative, and we assume seconds to be our metric, and therefore we multiply the difference times 1000 and divide it by interval. Here we sum up our error, and then in this part again we adjust for seconds, so that we don't measure the integral per interval but per second. We used to print everything for debugging purposes, but to use Python script we only print the position. We take the motor speed to be absolute value of our PID equation, and then if the motor speed is bigger than 5, we add the minimum threshold value so that the engine reacts immediately. And then if the motor speed is too big, is bigger than 255, then we make it equal to 255 and set the motor in movement in appropriate direction and with appropriate speed. This was Ignacy and Karol on the PID assignment.